Or any moment now. Yeah, all right, it thinks it's live. And then I hit record, and then we go into PowerPoint. Okay, all right, team. It's time to, have class. Nice to see everybody. Glad that we have a non-zero number of students in class today, despite homework due yesterday. That's always nice to see. In case you have forgotten, you had a homework due yesterday, but the good news for you is that there are late days in this class. So as a reminder, our late day policy is that you can turn in things late. And for every 24-hour cycle that uses one of your late days, there's some number that's in the syllabus, and if I say it wrong, then you guys are going to throw a fit at me, so just look on the syllabus and get the numbers there. And other than that, I think your next homework is out. I think that the homework that was just due, for me at least, is probably the hardest one in this course. So hopefully it's all, easy for you from here on out. So the next homework will be on physically based animation. After that, we have ray tracing, and then GPU stuff, and your final project, and a quiz, and you're done. No biggie. Any questions, comments, concerns? Yes? That's a good question. I think what we'll probably do is put it on the online thing, and you guys can just take it at home. I don't really see a reason to force everybody to come in the room and do something at the same time this year. Yeah. So it goes without saying that, you shouldn't cheat, would be my preference. Do recall that there is a midterm in this course. It's like shortly before the drop deadline, just in case. And there's also a final project. The final project is extremely open-ended, so you should read the instructions. And as you watch all the lectures in this course, kind of keep in the back of your head, like, these are the topics I'm excited about. And you can choose one of those to explore for your final project. So in your next homework, not the one that just went out, but the next one, you're going to have, like, in addition to the homework, you'll turn in just like basically a paragraph kind of proposing what you'll do for the project, just to make sure that you're thinking about it. Any other questions, comments, concerns? Like good restaurants in the Cambridge, Somerville area? No? Okay. That Mexican place. I know, but apparently I should. Mexican Felipe's in Harvard Square. I don't trust Mexican food in Boston. Oh, it's good? Okay, good to know. All right, folks, so with that, we're going to get started today with ray tracing, which is fun, really. The ray tracing algorithm is what's going to allow us to render all kinds of really beautiful scenes just with extremely high computational cost. And so that's our goal today, is to show some of the powerful things that we can do by essentially just reusing over and over and over again the same little segment of code for intersecting array with the object in our scene. So as a tiny bit of review from our last two lectures, remember that essentially what we've done so far is implement some version of ray casting. And remember that ray casting is this idea of, you put your little virtual screen in front of your eyeball, you send out rays into the world, you see what objects the rays hit, and those are the ones that you render. And for now, that was basically it, right? So once you figure out what's in front, you do some shading calculation and display that on the screen. And so, of course, in order to derive this ray casting algorithm, we did a lot of things in the last couple lectures, right? We talked about how to deal with cameras, in particular the pinhole camera and the orthographic camera. Remember the difference between those is kind of whether there's an eyeball or whether the rays all go in parallel. We talked about how to intersect rays with different pieces of geometry. And most importantly, we worked out ray triangle intersection in our previous lecture, which is really what allows us to render all kinds of interesting shapes. And then finally, at the end of the last lecture, just for fun, we talked about two features we could add to our raycaster that essentially are things that are like easy to implement in ray tracing and make for interesting geometry, despite the fact that we never actually represented the shape explicitly, right? So we talked about CSG and transformations. So transformation was the easy one, like apply matrices to our shape, and we just have to be a bit careful with the normal vector on the way out. And then CSG, anybody remember what that stands for? Yes? Constructive solid geometry, that's absolutely right. Sean, you're not Sean. Sean was at the end of my office hours. I don't remember. Ethan, I was close. Right. So remember that CSG was this interesting one where shapes were defined using like set Boolean style operations, and then we did it by kind of one-dimensional set arithmetic. Any questions so far about our scenario where we've the calculations we've already done here? Cool. All right, so today we're essentially going to kind of add to our library of materials and effects that we can get inside of our ray tracer or our ray caster by moving to this ray tracing algorithm where essentially once a ray intersects into a thing, oops, did I just pull out that cable? I might have. I totally did. Ugh. Okay, once we intersect a ray with an object in the scene, the ray tracing algorithm might send more rays out into the world to do additional calculations, right? So that's the basic difference. And that's going to allow us to capture some, but not all, interesting visual effects. So some of the ones that we'll talk about today include, I struggle with these words, reflection, refraction, and shadows. So certainly reflection and shadows are ones that you've encountered all the time. And then refraction is for like transparent objects where the ray kind of can bend what direction it's moving in based on the index, like the speed of light within the material as opposed to outside of it. So we're going to talk about all three of those things today, and essentially all of those are going to have to do with launching secondary rays out there into the universe. We're not going to be able to deal with two other effects, indirect illumination and caustics, which we're going to need a more advanced set of algorithms for global illumination to cope with. Okay, so that's our basic scenario today. Basically what we're going to do is figure out that there are a lot of lighting effects that sort of have a certain symmetry built into them. That's one way to think about the things that are kind of easy in ray tracing, right? Like the direction of a ray when you reflect it off a surface is sort of the same as if you reverse the direction, it would come back to you. And if you think about it, that's really what's making these algorithms work, right? Because in essence, light actually travels from the light bulb to your eye, but what we're doing in the ray tracing algorithm is going from your eye to the light bulb, right? And so we're kind of relying on that kind of symmetry to make our calculations easier. And that's why things like caustics, we're going to find that breaks down a little bit, and that's why we need some more kind of fancy calculation. Okay, so our overview for today, we're going to talk about shadows first, reflection, refraction, and then some of the kind of high-level concerns that come up with the ray tracing algorithm. Namely, we have this giant set of recursion, and anytime we have recursive code, we better be confident that it terminates. And so we're going to think a little bit about the computational expense, how we might limit it, and all that good stuff. Okay, so we already actually talked about shadows a couple lectures ago, but I'll go ahead and remind you essentially the ways that we can do shadows inside of a ray tracer, and I think the logic is pretty straightforward. Right, so we have our scene here. Here's our favorite kind of ugly diagram, right? We have our eyeball. We only know how to render spheres and cubes, so that's what we're doing today. And we send out a ray from our eyeball into the world. It runs into the sphere, and now we want to figure out if it's lit or not. Right, and this is the kind of thing we can do in our ray tracer. And when I say whether or not the sphere is lit, what I mean is whether or not it's receiving light from a given light source. So what can we do? Well, essentially, we need that little binary calculation, right? Did I get light from this light source or not? And the basic logic here is that, you know, if I'm receiving light from my light source, then I can draw a straight line from the point on the surface to the light bulb, and there shouldn't be anything in between. Right? I think that's a pretty reasonable piece of logic. And so that's essentially what we're going to do to add shadows to our ray tracer. So here's a little piece of code that I think all of you guys could probably come up with at home easily enough. So what could I do? Well, here essentially is a bit more code. You can think of it just for like shading an object, right? So I've run my ray into an object, and now I'm trying to figure out what color to make it. And there's a lot of different things that we might do. So this first line of code is actually a hack, but it's very common in ray tracing, where what you'll do is some objects will have an ambient color, meaning that even if all the lights are off, when my ray intersects that object, I just return that color anyway. If you think about it, that's completely non-physical, right? Like that would be like things that are radiating energy, which would be kind of concerning in most ray trace scenes, but it's a good way to kind of account for ambient light that's like bouncing off of things in indirect fashion without doing all this global illumination. But then the more interesting and important effect is to iterate over all the light bulbs and do like the kind of brighter shading. And that's what this for loop is doing. Okay? So what do we do? Well, for each of our light bulbs, we're going to make a ray, which is ray 2 here. And that ray starts at the hit point, like the location where the ray from my eye into the world hit into that object, but it's going to point toward the light bulb. Okay, so again, here's my light bulb, here's my surface, here's my eye. So I'm going to send this ray out into the world, right? That's what our ray caster is going to do. And now ray 2 starts at this point and points like toward the light, like that. Okay? So what do? Well, I then say, I can look in every single object in my scene, and if this ray 2 object hits any object in the scene, and it's closer than the location of the light, then I shouldn't do shading. Notice I need to be a little bit careful, right? Because like if there's an object up here, that's perfectly fine, right? So I need to check whether the t value of the intersection was bigger than the t value for this point here. And if it was, then I don't light it. Or, wait, that was backward. If the t value of the intersection is bigger than this, then I do. If it's smaller, then I don't. Ooh. Does that make sense? Have I managed to confuse you all by getting my inequality backward? I see a few furrowed eyebrows. Yes?
Is there a possibility that, like, the ray might, come back to me? I'll formulate.
All right, we'll keep thinking about it. Excellent question. Any others? Yes?
Yeah. I said we like or we don't like the point, but like shadows are more. We just don't know if we're gonna have like one black pixel.
Ah, yeah, that's an excellent point. So somehow there's something binary happening here, right? Either I'm lit or I'm not. And we know, I mean, if you look around this room, I think you'd be hard-pressed to find any shadow that's as sharp as what you would get in this setting. Did anybody have any idea? Like, what have we not accounted for in this model? Yeah?
The light might like bounce off of the surface.
That could be one thing. Like, you might be getting some indirect light, but that's actually not the main source of soft shadow. What was that? So several lights, you're right. So, but then you just get multiple hard shadows, right? So like, yeah.
I think the light like defocuses when you move the thing further from what's happening to the other one.
We're getting closer, so the light sort of defocuses. Think about why you have depth of field in a camera. It's actually a very similar issue. Yeah.
I was thinking like you have like really big lights.
That's right. Lights are physical objects, and they're not infinitesimally small. Right? And so here's what happens. I mean, our model for a light so far is this infinitesimally small point, and then it's completely unambiguous. Like if I have, I've been doing this thing where I pick up the chalk and then I put it there. If I have a surface down here, right? If my light is infinitesimally small, then there's this like kind of penumbra, whatever shape that goes right underneath it that shows me where the shadow is. The reason why shadows get soft is that in reality, lights take up a positive amount of space, and some fraction of this light hits the bottom surface, right? So like in the middle, 0% of the light is there, and as I move to the outside, essentially there's a drop-off where like maybe the light in the corners of this thing reach the point, and the ones on the inside don't. Does that make sense? Yeah, so that's what we haven't accounted for, and we're going to come back to that later in the lecture, and that's going to be something that's actually not so hard to fix. But you're right. So far, all of our ray trace scenes kind of look like interrogation rooms, like one sad light hanging off of the ceiling. Yeah. Excellent. Any other questions? Okay. Right. So now we have shadows, which is great. One thing that we're going to learn when we do rasterization, like GPU video game style rendering, is that shadows are actually a huge pain in the tuchus. They're like one of the harder effects to implement. And in fact, your entire fifth homework is going to be to implement shadows inside of a GPU rendering pipeline. So it's kind of interesting that in essentially like 5 extra lines of code in your ray tracer, you can get this kind of effect, but at substantial computational costs, right? That's, as always, that's the usual story. Yeah?
So does that mean when you're initializing your light object, you need to specify like the size of the
That's a great question. So if your light source is an ideal point, then no. I mean, I still have to say the location, but not the size. In reality, you're absolutely right. There's a whole, just the same way, like if I set up a scene on a stage somewhere, right, there's a whole different types of lights out there, like spotlights and area lights and so on. Essentially, for each of those, there's a different model that you might use in ray tracing. So it's very much like the physical setup. In fact, there are people whose full-time job is to do like lighting for virtual scenes, and it's an art form, just like in theater. Yeah. Any other questions? These are all great questions. Well, minus one, but we give you one. Just kidding. All right, excellent. So there's one small bug that can happen. This is a very typical ray tracing issue, so it's worth highlighting now. So here's the basic problem that can arise. So I send the ray out of my eye into the world here. It runs into this object. I launch my secondary ray, right? So I now create a ray that's at this location and toward the light. Well, remember that all of the computations we do in our ray tracer are based on floating point arithmetic. And whenever you do floating point arithmetic, there's like this giant elephant in the room. That's a poor use of that phrase, which there's a giant problem that can arise, which is rounding, right? Like none of the calculations that we do here are infinitely precise, right? And so, for example, I might have computed this intersection point, but just by bad luck, maybe the intersection point is ever so slightly inset in the interior of the sphere. It could happen, right? Just thanks to rounding. Well, now I create that secondary ray pointing toward the light source. What's going to be the thing that that ray runs into? The sphere itself, right? Because I got it slightly wrong, and now it just bumps right back into the sphere. So then what's the conclusion that I draw? Like, aha, I should be shadowed. Yeah? So this is actually a common artifact. This is called self-shadowing. So here's an example of it on the left, where essentially what'll happen is you'll get this random pattern of like dark speckles, because every once in a while when you do that shadow calculation, you kind of come to a bad conclusion, which is that like the surface itself is the thing that's shadowing itself. That was a poorly phrased sentence, but I think you guys understand what I mean. And so the sort of typical thing to do is like, usually, you know, we've talked about ray object intersection. You want to make sure that that t is bigger than 0. You may actually want to check that that t is bigger than some like positive epsilon to make sure that you're kind of offset from the surface a bit. An alternative way to fix that bug would be to take that source point and just like displace it a bit along the ray. Either one of those is kind of equivalent. Any questions about that? Yeah, so this is one of these kind of things. So as you write your ray tracer, you'll undoubtedly see all kinds of weird visual artifacts like what you're seeing here. And then here's my challenge to all of you as you write your code. This is just generally true in this course. It's also true for your physical simulation assignment. Is like you're going to see a bug, like your simulation diverges or your ray tracer makes some weird artifact. Don't just start throwing spaghetti at the wall and like changing your loop iterations to like plus and minus 1 and like maybe dividing, multiplying, scaling, whatever. Like step back and like think and say like, okay, what is this? You know, my ray tracer is trying to communicate to me that something has gone wrong. Like what could have broken? And I think that's a much more effective debugging strategy in graphics in general. There's my high-level life advice. Okay, so that's the basic shadowing algorithm. Essentially, it's just a few extra lines of code, and notice that it's really making use of that nice abstraction that we already had in our ray tracer, that an object is a thing that can accept rays. Right? An object is just a thing that has a query saying, does this ray run into it, and if so, where? Right? And just by reusing that piece of code, we now can not only shade objects in front of the camera, we can figure out if they're shadowed or not. But relative to that abstraction is absolutely correct, but it may not be the fastest way to do shadow computation. In particular, let's say that I'm lighting this point P here on this sphere, and there's two different objects that are between the sphere and the light source. Now, remember my ray tracer so far, what do? I like loop over every object in my scene, and I check if it intersects that ray, and then I kind of keep the closest t, all that stuff that we're getting pretty good at. But here's the thing, if I found that triangle first, do I need to continue my for loop? No, right, because I already have evidence that something is in between me and the light source, right? And so one thing that you can do, which is pretty typical, would be to actually make two different intersection things. So in other words, when you write that like ray object intersection code, you might make a different one, which is just binary, like does this ray intersect me or not? And maybe you don't do the most precise calculation for exactly where, because you just want to see if it's closer than the light source, right? And so this is one way to make your code a little faster, and I think it's a pretty typical fix. Any questions? Excellent. So here's a picture of what we can do so far. Actually, it's not entirely accurate, I guess. Well, is both of these reflective? I actually can't quite tell. Yeah, I think they are. Yeah, this scene we can ray trace now. We've got shadows and reflections. Okay, anybody remember what this scene is called? Fun review question. This is the Cornell box. Because guess where it was made? Harvard, yeah. Sheesh. All right. Right, so that's it for shadows. So now let's talk about reflections. We're going to start by talking about really shiny, polished mirror-style reflections. And then we'll talk about how we might make more everyday kind of scrubbed-looking material, which is what we actually have. Right? Because an ideal mirror is actually an object you like kind of can't see, right? Like it just is like reflecting something else. And obviously the mirrors we interact with in everyday life, I think you would know that there's an object in front of you. It's not just like a portal into the dimension behind. Right, so mirror reflections are handled very similarly to shadows, but now you're going to make a secondary ray for the purpose of shading rather than just lighting, right? So like you'll make a ray that's basically the bounce off of your from your eye off of the object into the world to figure out the color, right? So we're going to work out the details. Notice that self-shadowing also has a similar effect for mirror reflection, right? If we bounced and then ended up in the interior of our sphere a little bit or something. Right, so in order to do mirror reflection, I don't think actually technically you guys see this in your physics class because your physics class is mechanics, right? But I think the law of reflection is a pretty natural one. It's sort of like, you know, if I asked you to sit down and guess what a ray probably does when it reflects off a mirror, I think we would all guess the same thing. So in particular, here's what goes on. So R is the direction of the reflected ray, and V is the direction of the ray from the viewer. And essentially what happens is there's a nice symmetry, right? So you take this ray from your viewer onto the surface, and you just reflect the component of that ray that is normal to the surface. That make sense? So in particular, this V dot N times N term, does anybody, can we kind of intuit what that is? What are dot products? What are they doing? They're like giving projections, right? Yeah, so I think the right diagram to draw here, right? So here's our surface. And by convention today, our ray V is pointing into the surface like that, right? It's not just convention, it really is probably what happens in your ray tracer, right? Because V is coming from your eye to the surface. The surface has some unit normal N, like that. And so essentially the law of reflection says that like the component of V that points into the surface just gets flipped and everything else gets left alone, right? So what does that mean? Well, if I wanted the component that points into the surface, I'm going to take V and displace it so that its foot is sitting here, right? Then this vector that points down like that, right, if this is 90 degrees, what would that vector be? Yeah, that would be given by the dot product. That's absolutely right. So you have V dot N times N, like that. So if I want to get the reflected ray, what do I have to do? Well, I kind of have to cancel this thing out and then add it again to get a component like that. So that's where this factor 2 comes from. Right? So then the reflected ray is like V plus 2V dot N times N, right? The formula on the slide here. That's wrong. That's a minus. Because this is pointing down, so I need to point up twice. Okay. Any questions about the picture here? Yeah. Why does it have the bottom one pointing up? Ah, yeah, because there's a minus here. Yeah, that's right. So my diagram is pointing down as V dot N times N. This one is pointing up because it's minus V dot N times N. Yep, good call. I really should look at these things before I start writing on the board. It would be much more consistent. It's good. We're working on problem solving. Any other questions? I think this is a pretty reasonable one. And notice that this is something that's easy enough to implement in your ray tracer code, right? Because the ray tracer already gives you the normal to the surface. We were using it for shading. The V is given by the direction of the ray, so essentially this is a pretty easy formula to just type in. Right, so what would you do in your ray tracer? Well, if the ray hits into your reflective surface, you just generate this reflected ray and kind of keep going, right? So the color that you would return for this point would be the color that you get for this ray that came out. So again, this is kind of recursive, right? It could be that that ray runs into some other reflected thing. Any questions? Yes?
Could you explain the colors again? Because, like, are you saying, like, the light that hits the surface is then, because, like, the color works because light bounces off and that color is absorbed and reflected back. So are you saying that the outgoing ray is the color of the surface?
Yeah, let's think through that a little bit more. I can draw a picture of what I mean. So let's say that I have a reflective surface. It's always really hard for me to draw this in a way where it kind of works out. So let's say I have a non-reflective object, and I have a reflective surface underneath it, and I'm a mathematician, so I'm looking at the ground. Okay, so right, so I want to render this thing, and I see an image of this sphere in this mirror, right? So the question is, what's going on? Well, in reality, as you say, maybe there's like a light source here or something, so there's color. What's going on? Like there's light bouncing off of the surface, and then going down like that, and going to my eye, right? But the way the ray tracer works is sort of the opposite of that, right? This is why sometimes we use the phrase backward ray tracing. So the idea is that I launched a ray out of my eye, it hit this reflective surface, so what do? I generate this secondary ray using the law of reflection, and I just query the color that this secondary ray has. And now that's the color that should be associated to this point on the surface. All right, does that make sense to everybody? Any questions? Now, if that were really how mirrors worked, I mean, we'd have a lot of trouble brushing our teeth in the morning because, like, you know, you'd brush your teeth and you feel like you could, like, reach in like that 80s music video and, you know, go sucked into the mirror universe. The reality is that, like, you can see the mirror in front of you because mirrors are not perfect materials. There are many ways to kind of account for that, right? Like, it might be that you take this color and you attenuate it a bit and add it to some other color that's associated to the surface. Or we can do more complicated BRDF tricks, which we'll come back to later. There are lots of interesting effects that are actually not so hard to account for, but can make your ray tracer a lot more realistic. So here's one. So this is a trick for figuring out how much reflection there is. So again, basically the point is that there are very few perfect mirrors out there in the universe. Most things, the amount of reflection depends, for example, on the viewing angle. So in order to really do that, there's something called Fresnel's, I think it's Fresnel's law, Fresnel's something or other. Essentially, Fresnel is the name. When you hear Fresnel, it has to do with how much reflection is coming off the surface. And the basic point is that, like, when rays graze a surface, R-A-Y-S space G-R-A-Z-E, they tend to reflect more, whereas if I look straight down on a surface, there tends to be less reflection. And notice that our, like, perfect mirror doesn't really account for that. This surface actually happens to be a great example. You guys can come and play with it after class, right? If I look at it at this angle, not only am I going to have trouble standing up, but also it looks more shiny than if I look straight down. It just looks like a diffuse object. And there's actually the floor is another good one. So, right, so a typical thing to do is to kind of work out that angle, right, between the normal and the direction to the viewer, and then to use that to attenuate how much reflection term you have for your material. The actual rule for doing that, this Fresnel formula, is quite complicated. You can look at it on Wikipedia. In graphics, we're all about weird approximations, and conveniently, somebody named Schlick, I have no idea who that is, managed to guess this weird formula that roughly, like, 1 minus cosine of the angle to the 5th power happens to be a pretty good approximation of the true behavior. Why, you might ask? I think literally Schlick just guessed formulas until he found one that matched, he or she, I really don't know. And it's a very Schlick approximation. But it's a convenient formula because you have that cosine anyway, right? Like it's just a dot product. So this is a pretty easy thing to implement, and it makes a substantial difference in the look of your material.
You look forward to that joke every year?
Absolutely, yeah. You know, like this course is recorded on YouTube, and I'm sure you could find at least 6 different versions of it. Okay, so yeah, so now our sphere fractal image can have like slightly shiny, weird spheres instead of just diffuse ones from before. So our ray tracer definitely has some progress here. Any questions about reflection? This is like our little mini physics lesson for the day. Okay, so the next thing that we're going to deal with is refraction, which is the sort of thing that happens with like glass material, you know, things where the ray goes through, but the direction of the ray might change. You know, we've all experienced this, like when you look on like, you know, surface of water, right? This is the usual phenomenon. Like if you're a spear fisherman, apparently this is a big problem in your everyday spear fisherman life. You know, like when you jab a spear into the water, it like looks like it bent, right? Because of just this law of refraction. I guess if you're a spear fisherman, you have to somehow correct for that, solve a mildly nonlinear problem to get the fish. But in any event, in ray tracing, we can simulate this and have these nice underwater scenes in a way that looks better. The basic point here, again, is going to be that our light is following this path, which is nonlinear, because it turns out that the path of light is affected by the material around it, right? Namely, the speed of light. And so we can do things like try and capture this Pink Floyd album. Actually, all rendering people use this as the example, but the reality is that most ray tracers can't handle this scene because notice that a rainbow comes out of the side. And the reason for that is that refraction is actually something that depends on wavelength. And very rarely do we actually account for wavelength in a careful way in our ray tracers. So it's actually quite difficult to get this effect correct in a basic rendering tool. And it's extremely expensive to do it correctly computationally, right? Because suddenly you have your ray tracer kind of multiplied by the number of wavelengths you want to account for. Okay, so essentially what we want to do is deal with transparent type objects. And algorithmically, it's quite similar to how we deal with mirrors, right? Like, remember when we have this reflective material, essentially we just bounced our ray and kept going. Now, instead of bouncing, we need to go through the material and keep going that way. And so, and incidentally, typically, again, there's like some coefficient. So you like, you know, refract and then maybe attenuate that light a little bit just to make for a nicer material. In fact, I mean, a lot of materials are both reflective and refractive, right? I mean, if you look on the surface of water, you know, there's some reflection and you can see through. So maybe you actually do both of these things and scale them by different numbers. And, oh, right, and there again is our, actually this is a more peaceful environment, I guess. You're just observing the fish rather than trying to spear it, which is good because the octopus, I feel, is a higher value target. Okay, right, so let's talk about the law of refraction. I always learned this as Snell's law, but actually it was discovered earlier than that, but just didn't happen to be in Western Europe. So of course we ignored it by somebody by the last name of Saul. So we should all go back and revise our physics textbooks. But the basic point here is that when light enters a material, basically what determines the angle of the light ray has to do with the ratio of like the speed of light on the two sides of that interface. And so the way that we typically measure that is we associate our material with something we call the index of refraction. And then this law, which depending on what physics class you took, is Saul's law, Snell's law, or apparently in France is Descartes' law, which that third one is unambiguously wrong. The second one, at least in like Western Europe, is correct, and the first one is really correct. But the third one is French, so in France we learned Descartes' law. It must be confusing having all these Descartes and Poisson rules, you know, at some point you'd think somebody else would have thought of something. In any event, right, so the ratio of the sines of the angles is exactly the ratio of these indices of refraction, right? Sometimes that ratio is called the relative index of refraction, which kind of, you can think of that as sort of describing the interface between two materials, okay? So I think this is a rule many of us have encountered in physics class. Certainly if you've taken optics, this is like a kind of basic one. It's perfectly fine for calculations on paper, but it's actually kind of annoying in your ray tracer. The reason being that like, this isn't in coordinates, right? Like you guys actually need to figure out the direction of your ray, and this thing is just like describing angles. And so we really do need to do a little bit of work and take this nice kind of elegant formula and make a much uglier one that actually describes what's going on in a way you could type into the computer. So that's what we got to do here. Incidentally, my colleague at I think Dartmouth recently kind of brought this little name change to my attention and kind of tracked through some of the history here. So it's a bit fun to read through his little Twitter post. Okay, so right. So let's actually work through Snell's law here and see if we can come up with a formula that actually we could implement in our ray tracer, right? Because like we don't actually have theta I and theta t, and that doesn't really give us the coordinates of the ray that we're going to need to implement. Okay. Unfortunately for us, this is a bit of annoying math, but that's okay. That's why we're here. Okay, so let's draw a picture of what we're doing. I actually have notes this time because I'm bad at math. Okay, so here's our refractive surface. And as usual, our surfaces have normal, so that's going to be big N, like that. Any questions so far? Okay. And we're going to have a ray just by, I would say by convention, it's not even by convention. By my laziness, I'm going to choose to have my vector point toward the viewer. I'm going to highlight that now because when we did reflection, we had it point from the viewer. This is just because that's the way I wrote it down in my slides, and it's too late to change now. That's why. Okay, so we're going to call that vector I because it points toward your eye. Okay, right, and we can make one more vector, which is going to be kind of convenient. I'm going to call it M. And the way that we can think about that is that I and N together form a plane, right? Because they're two vectors. So I'm going to make M be the vector that is orthogonal to the normal and is in the IN plane, like that. Does that make sense? So M is going to be tangent to my surface. Okay, so first of all, so by definition, this theta I thing is sitting right here. This M vector is just for convenience. It's not really something that we have access to. I mean, we could compute it easily enough, but it's not something that we have in our ray tracer. So we're going to have to compute it. But conveniently for us, that's not terribly difficult. So in particular, we're going to do lots of right triangles today, our favorite kind of triangles. Actually, they're not great for finite elements, but let's take my graduate class for that. Okay, so let's write a formula for this vector I in terms of theta I, N, and M. Okay? So in particular, I can write I as the component parallel to N and the component parallel to M, because these two things are spanning this plane here. So what's the N component in terms of oh, I just said it. In terms of theta I, cosine, thank you guys, you're so brilliant. So this is, that's absolutely right. So this is N cosine theta I. And what's the remaining part in terms of M and theta I? What was that? That's right. So it's minus M sine theta I. Notice that it's a minus because I chose the convention that M points to the right. Everybody with me so far? This is just trigonometry. Okay, so let's rearrange this a little bit because M is really the vector that we don't know how to deal with. So we can solve for M here easily enough. And what are we going to get? So we can add this to both sides and subtract I from both sides. Yeah, and we're going to get that M is equal to N cosine theta I minus I, all of that divided by sine theta I. Right? So this is just, I just rearranged this expression here. Okay, so that's good because essentially N and I are the things that we have on hand, and what I've done is convince you we could also compute M, at least if we know theta I, which we don't necessarily, but we're going to see that there's an easy way to deal with that later. Okay, so at the end of the day, the thing that we really want is T, so let's continue to draw our picture here. So let's take the normal vector and extend it the other way. That gives us the direction minus N. And we have T for transmitted, which is some vector like that, right? And we have theta T down here. Okay. So to start, let's do something similar to what we did on the top and just write an expression for big T here in terms of our basis vectors here. So who wants to help me out? What's big T in terms of theta t, n, and m? I know you guys can do this. I can see your hand. Maria, help me out. Yeah. Negative n cosine theta t plus. That's absolutely right. Thank you. Okay. Everybody with me so far? Okay, so now I'm going to take our expression here and plug it in, just to make our formula as ugly as possible. So let's go ahead and do that. So we'll leave that first term the same. So we got minus n cosine theta t. And now we've got sine of theta t. And notice that there's a sine of theta I here. This is feeling promising, right? Because like there's a 1 over sine and a sine, and that kind of looks like Snell, Descartes, Saul, whatever's law. Okay. So what do we get? We're going to get plus n cosine theta I minus big I, and then all of that times the ratio, right? Sine theta t divided by sine theta I. Cool? All right. So now we're cooking with gas. So first of all, what is this? What is that? Yeah, this is Ni over Nt by the Saul's law here, otherwise known as the relative index of refraction. So let's call this N sub r here, which is good because like angles are annoying, but constants aren't so bad, right? So we just got rid of 2 angles in one shot, so we're doing all right. And by the way, notice that it's also good because like somehow cosines are mildly easier to calculate because they're like dot products, right? Sines are like slightly more annoying. Okay, so that's that. By the way, this isn't really an n; it really should be an eta, like that. Yes.
But like when you're actually doing this in a ray tracer, would you have to find like data, or would you like to know that?
That's a good question. Yes, the question was like, you know, what do you actually know? Do you know the eta, like eta I and eta t, or eta r? The answer is you probably know eta I and eta t as like sort of the material my ray is currently in and the material my ray is about to enter. But it certainly wouldn't be too hard to compute eta r. The one thing you have to be a little bit careful about is like, am I entering or exiting the object? Because you'll either get eta r or minus that, right? So that's where the normal to the surface is useful. Okay, so now let's regroup this expression a little bit. I'm going to take all the things involving n, and I'm going to put them into one term, and I'm going to take all the things involving I and put them in another. Okay, so what do we get? Well, let's see. So we're going to get, we'll get eta r times cosine theta I minus cosine theta t. That's everything in front of n, right? So again, that's eta r times cosine of theta I, and then minus cosine theta t, it's a t, all that times n. Okay. And then the I term is not so bad. It's just eta I times I. Okay, so we're just doing algebra. All right. So, now what? So now we're going to do a bit of a few trigonometric sleights of hand to make our formula a little bit easier to work with. Notice that, by the way, these are all things we could implement in our ray tracer. There are many different formulas you could use, and we're just going to derive a standard one. Right, so in particular, if we have an angle theta, what do we know about cosine squared theta plus sine squared theta? It equals 1. Thanks, guys. It equals 1. So in particular, we're going to do something kind of funny. And that's the following. So we don't really know theta t, right? Like when we're doing our ray tracer, what we probably know is theta I, right? That's the ray coming in. So one thing that we can do, well, we know the relationship between the sine of theta i's and the sine of theta t. But unfortunately for us, we have a cosine of theta t here. So what could I do? I could kind of engineer this a little bit. Well, I could stick a sign here by applying this rule, right? Notice, by the way, that our theta is always between like 0 and 90 degrees because of the way we've drawn this picture. So we don't have to worry about the SIGN too much here. All right, so let's swap this out so I don't have to bend over. And we can keep going. Okay, so in particular, what we're going to do is we will leave the first term alone. So we have a to r cosine of theta I. And now we're going to do minus square root of 1 minus sine squared theta t. All that times n minus a to r times I. Right, everybody see what we did there? Sneaky, huh? Because what can I do with this? Well, what is sine squared of theta t? Well, take a look here. I know you guys know how to do that. So we have the ratio between theta t and theta I is equal to a to r. So what is this thing equal to?
If you move like that theta t over and you change it to theta, the a to r, so
Yeah.
it becomes a to r times sine theta I squared.
Yeah, that's absolutely right. Yeah, so we're going to have this is really equal to a to r squared times sine squared theta I. Everybody was awfully quiet there. So do you have any questions about what I just did? We're just being shy today? Okay. Cool. So unfortunately, so now we're starting to do pretty well because notice that we've now eliminated all of the t stuff. We're dealing all with just incoming data. So we're like slowly getting to the formula that we might want. But sine of theta I is kind of annoying to work with, right? Because like, I don't know, you have to figure out how to compute sine. But we're pretty good at cosines, right? We're pretty good at dot products. How could I do that? Well, we have sine squared. I know you guys know where I'm going with this. Sine squared of an angle is equal to 1 minus cosine squared. That's right. Thank you, guys. Put me out of my misery, please. This is the same as 1 minus cosine squared theta I. Cool? All right. Now we're basically done. So let's write this in a different way. So what is cosine of theta I in terms of the vectors that we have on hand? Yeah, so we have, remember that like I and n are the information that we have. So assuming that those are unit vectors, how could we get cosine? I dot n, thank you. Okay, so that leads us to our final formula here. So in particular, we have the following. We have a to r times I dot n, like that, minus the square root of 1 minus a to r squared times 1 minus I dot n squared, like that. All that times n minus a to r times I. Everybody agree with me? Excellent. So notice that this formula is ugly, but it's completely in terms of stuff we have on hand. Do you see that? And that's really what matters, right? Because essentially when we're doing our ray tracing, right, I is like up to sine, SIGN, just the direction of the ray, right? So that's like input data. And n is the normal to the surface. And basically what I've given you here is just a formula for how to get that new direction out of those guys without computing a bunch of intermediate variables and doing cosines and sines and everything else. Okay? So here's a tidier version of exactly the same math. But any questions about what we did? You guys are awfully quiet today. I'm suspicious. Yes?
So we did write all of these because it's faster to implement, because it's just
Yeah, I mean, that would be fine too, right? I mean, you could have gone through and tried to compute the actual thetas and then compute their signs and actually work through this law, and that'll be equivalent to this formula. The reason why you might want to do that is that this is faster and cleaner and doesn't involve so many steps. It's just like a direct formula rather than a bunch of intermediate stuff that you didn't actually need. Yeah. Excellent. Any other questions, things I can help y'all with? Cool. So as always, this is yet another annoying formula you have to type into your ray tracer, and that's just life in the city.
Probably learn it more intuitively once we have to type it in.
I'm not so sure about that. I don't think this is a very intuitive formula. I think it's just an annoying thing you have to type in.
We'll understand it better once we have to implement it.
I'm not convinced, actually. I think there's not much to understand here. I think this is actually just a formula that you have to type in, but I could be wrong. Yes, not Sean. Ethan.
I was about to say, it's literally just this way because this is just the info we have on him.
That's right. Yeah, there's nothing special here. This is like if you took a physics class, like essentially we took an elegant law from physics and made it ugly. This is because we're just working with the data that we got. Excellent. Okay, guys. So yeah, so that's refraction. Now remember, anytime I write down a numerical rule like this, I need to do a bunch of sanity checks and make sure it makes sense. What could go wrong with implementing a formula like this? Like remember, like for example, we often get sensitive about dividing by 0. Corey, what could go wrong? Yeah, the square root could go negative, and that would be a problem. What should we do in that case? Should we make an imaginary ray? No, the surface just goes black. I'll give you a hint. So anybody know how like fiber optic cables work? They actually rely on that thing being negative. So there's a physical phenomenon called total internal reflection. So in total internal reflection, a really interesting thing happens. Sometimes in 6837 we demo it, but Wojtek Matusik wasn't around this morning, so I couldn't break into his office and get the little demo thing. But I do have a picture of what the demo would look like were we able to do it in class. Essentially, for refractive material, when the ray hits a sort of a grazing angle, there's this sort of critical angle that happens where suddenly the ray will reflect in the interior instead of refracting. So kind of like the interior boundary starts acting like a mirror instead of a refractive material. So you can actually do a fun experiment where you like make an object like this, and then you change the direction of the light, and what'll happen is for a while it'll come out the bottom, and then suddenly it'll bounce back up. And that phenomenon happens precisely, of course, when the direction of the refracted ray kind of aligns to the tangent to the surface, right? Because then it doesn't make sense to refract anymore. Any questions about that? So in fiber optic cables, you have like one long piece of refractive material, and it's really, really thin. So when the signal goes down, it kind of bounces its way down the cable. So that's my very abstract understanding of what goes on in fiber optics. I'm sure there's much more to it. Okay, so when we deal with refractive materials, it is a bit annoying to deal with some of the details here. I think Ari actually raised an interesting point. We have to be quite careful about whether you're entering or leaving a material. So like if you talk about the relative index of refraction, it's not enough to just say the relative index of these two things next to each other is like 17. You need to know it's like, am I entering or leaving which material, right? Because that'll tell you which one's in the numerator and which one's in the denominator. Luckily, that's not so hard to figure out because you have the normal to the surface, and the convention is usually the normal points out. So you can kind of figure out which ratio makes sense from there. There's one thing that can happen in the virtual world that can't happen in the ray traced world, which is that you could have two objects intersect. In that case, this law makes no sense because the physics also makes no sense. So in this class, we won't ask you to do that. In the reality, if you're making an industrial ray tracer, you have to come up with some reasonable policy for what to do in that case. There are all kinds of fun refractive demos, things to look at. Here's one that's coupled with a fluid simulation. And you can see, obviously, the law of refraction really makes a big difference. You know, if you didn't do it properly, you'd see right through this cup of water, and it wouldn't be a very interesting simulation. So obviously, the simulation people and the ray tracing people need to work together. Fluids are particularly tricky because, of course, refraction depends on the surface normal, and actually, typically, you don't often have a reliable surface normal in fluid simulation. For example, if you do it on a grid, So you need like a little bit of convention there for precisely how to ray trace and render this stuff. Cool. One final footnote about refraction. There are many different ways to derive it. Physically, it turns out that refraction has to do with the sort of ratio of the speed of light in your material versus outside, right? Like speed of light is pretty fast in air, and I think it slows down in pieces of glass. In fact, actually, if you take a physics class, you might derive it in a very different way. So, for instance, let's say that somebody's in trouble, like my colleague Fredo. He's swimming, and he's somewhere in the water. At least for people like me, swimming is relatively slow. Running on the beach is also slow, but slightly less slow. So it might make sense if I'm trying to get to Fredo as quickly as possible to actually run farther along the beach and then swim a shorter distance, right? And one of these, essentially one of the ways to sort of understand and derive Snell's law is that it's trying to compute shortest paths in the presence of physical speeds being different on the two sides of the interface there. Just fun fact. Okay. By the way, if you were to deal with materials that were non-uniform, like I make some, fluid where I'm swirling around things of different densities and the speed of light is like somehow a nonlinear function, then this would be the more general problem I would need to solve in order to come up with like a curved shape of a ray that moves through a continuum object like that. I think there are very few ray tracers out there that deal with that kind of thing correctly. Okay, so to extend our discussion a little bit, we could ask about wavelength-dependent effects. For instance, rainbows, of course, are things that we like to render. Does anybody have any idea, like, what's the standard way that one might render a rainbow? Any idea? Even? That's right. The standard way to render a rainbow is probably take a photo of a rainbow and just like stick it in the back of your scene. But if you actually wanted to do it with a ray tracer, you could. It would just be a little more challenging. And the reason is that rainbow-style effects are essentially using the fact that refraction is wavelength dependent. In other words, like the speed of light can vary based on the wavelength and the material. And so I think in particular, there's more refraction with less wavelength. I'm not a physicist. These are the kinds of things I have to Google if I ever wanted to implement them at home. And of course, that's what explains things like this prism experiment. Basically, in graphics, we tend to ignore this because we just attach to our rays like an RGB color. And whereas if you really wanted to do this, you would need like different ray directions for each wavelength and so on, which is quite hard to capture. There are many efforts in graphics to do rainbows and these sorts of, like oil slicks is another good example, because of course those are things that we see, and also it's a good, just challenging test case for rendering people. Anybody have any idea specifically for rainbows? What causes that effect, by the way, just for fun, beyond refraction? Yeah.
Like goes in and then it reflects back. It like doesn't hold. It doesn't absorb any particular wavelength.
Yeah. So it turns out that it's actually a combination of reflection, total internal reflection, and refraction in a wavelength-dependent way that causes this effect. So here's a kind of diagram of what's going on. So essentially, when you see a rainbow, really you have like lots of tiny particles of fluid floating in the air, and water has a different index of refraction than the air. So what happens is the light ray enters this thing. It's bending in a way that depends on the wavelength because that's what materials do, and then it's getting reflected back out toward the viewer thanks to the total internal reflection effect. Apparently, the magic number is 42 degrees, but I don't think that really matters. And that's essentially the reason why you're seeing this kind of thing. Notice that this would be, again, just really hard to capture with a ray tracer, right? Because like you'd have to trace rays in lots of different directions and colors and things to get this correct. Okay, here's another diagram of the same thing. But people do manage to do it, and you can get extremely subtle rainbow effects. If you look really closely at this photon mapping example, there's a little tiny rainbow sitting underneath that surface. There are probably more clear examples out there on the internet. But again, I think when you see the really giant, obnoxious rainbows in animated films, they're rarely done with like ray tracing or like some physically accurate thing. I think the more typical model is basically a billboard that's sitting in the back and just probably even pointed toward the camera no matter where you are, like just totally boring stuff, like environment map. There are many applications of these kinds of calculations. It's important to note that not all of them are rendering. So for example, if you want to design interesting camera lenses, ray tracing actually comes up quite a bit because exactly these sorts of rules, right, reflection and refraction, are what you would use to predict the type of image that you'll get by designing a lens in a particular shape. And so these days, when you buy a modern camera, really your lens shape is being designed really carefully in CAD software that's being built on the sort of calculations that we're doing in class today. Of course, the challenge there is that they really want to solve an inverse problem. Right? Like what you care about is an image formation model based on like what's coming out. And so you need to invert all of this stuff. But really, ray tracing has totally revolutionized the way that people do this sort of lens design. If you like this sort of thing, you should take 6815 or 865, which is Fredo's course. I think it happens like right before, right after our lecture here, which covers all this stuff in all kinds of detail. Actually, closer to my research instead of Fredo's, there's a kind of fun similar application which couples these calculations with a fun area of math called optimal transport, which happens to be what I work on. Let's see if I can get this to load, which has to do with caustic design. I think this is such a fun application. So the idea here is that if I have a piece of glass, I can like shave its surface in different ways and get really interesting patterns underneath, which have to do with the caustics, like the paths of the rays of light through the material onto the receiving surface. And of course, there are many different interesting patterns that you can get. Let's zoom forward to some interesting results. So what these folks tried to do is actually control the image that you get on the other side of the piece of glass by kind of focusing the rays of light in a particular pattern. So this is a really challenging inverse problem, right? So you know the position of the surface, and what you're trying to do is to work backward to kind of modify that surface normal ever so slightly to focus light in different ways, right? And so essentially what's behind this thing is just solving, applying Snell's law or applying, well, whatever you want to call it. And then solving using what I would argue is basically backpropagation and machine learning, like differentiating through the shape of the surface to get the desired pattern you want on the other side. I think there's a lot of really fun questions here. So for example, one thing that I've always thought about, like when you look at these examples, I think what's really funny is like, as you rotate these surfaces, somehow the pattern changes. And I'd really love to know if there's a way to like make some weird version of animation where you rotate a piece of glass and control the caustics in a really creative way. But anyway, yes? Oh no, that was an actual piece of glass. Yeah. The tricky part here is coming up with an objective function. So like it's easy enough to take your rays of light and simulate the image that you're going to get on the other side by doing ray tracing style stuff. But now, you know, my image doesn't quite look like Einstein. And so the question is, how do I change the surface to make it look more like Einstein? And that's where this area of math optimal transport starts to come in. In fact, I think this semester, the math department has an optimal transport seminar for undergrads. So some of you guys might be seeing there. The important thing to note is that transport is actually useful. It's not just a thing that math people do. But I think that sometimes gets lost in that department. Anyway, so there's a fun application of this stuff. Okay, so there's a few effects that we can get in our ray tracer, but of course we just step back and hold up for a minute and say, well, do these pictures look real? I mean, like these are essentially the kinds of things that we can render using the algorithms we've developed so far. And I think we'd all agree that this doesn't really look like real life. In fact, these look like 1980s computer graphics, because that's like roughly where we're at so far in our lectures here. And there's many things that have gone a tiny bit wrong. I mean, no surface is a perfect mirror, no material interface is perfectly smooth. There's this roughness everywhere. And in fact, there are many different models for that, right? Like essentially, the materials that we have so far are perfectly specular, or perfectly reflective. And the reality is that there's a lot of noise, right? Like sometimes we talk about being like micro changes in the normal vector to your surface that happen along the surface and are really what we need, right? So the reality is that one ray goes in and many rays go out just based on like these kinds of perturbative effects. And these make a huge difference. So for instance, if I want to render materials that have this sort of brushed metal look or this sort of cloudy mirror look, then I probably can't quite use the algorithms as I've described them to you today. Does that make sense? Like at least the problem we need to solve? Yes.
Yeah, but if you go back to the slide before,
Mm-hmm.
if you start to multiply the number of rays, it gets more complicated.
That's right.
Could I just like add some random noise on each ray,
Mm-hmm.
hoping that in the end,
Yeah, so that's a great suggestion, right? So it's going to turn out that essentially the way that we can solve a lot of these problems is by some kind of randomness. And the question is what's the right kind of randomness? So that's absolutely the right intuition. So here's a different way to view that. So here's the sort of reflective surface that we've described for you so far. So here, if I'm looking down at a perfect mirror, I've got these three colored objects. We have this nice scene on the bottom, which is really perfectly colored. But the reality is that we probably have things that look more like this sphere that we have here. And the reason for that is that there's sort of scattering in the normal direction, like we suggested, and we need to account for that, right? And so one thing that we could do is compute that reflected ray direction, and then maybe just perturb it a little bit randomly before computing the color. And that actually is roughly what we do to get this nice brushed material look, right? So you compute the reflection, then you perturb and do your ray tracing, and that'll actually give you a nice brushed metal look. Can anybody anticipate a problem with that? Well, think about like two adjacent pixels, right? They both probably run into that mirror, but they easily could get two very different random directions when they bounce off because of that. So what's that image going to look like? Yeah, it's just going to look like white noise, right? So the reality is that you probably have to repeat that process many times on average.
Is that why, like in rendering software, for example in Blender, you can see like the image kind of forming out of like.
Yeah, that's absolutely right. So oftentimes when you run rendering software or Blender or whatever, and it's doing some ray tracing, there are many passes over the image, and maybe even and oftentimes what it'll do is kind of do a hierarchical thing, like send more and more rays. And as it's doing that and averaging more, you can get a higher resolution and less noisy image. Notice what's going on when you run that software. A, it's really slow, and B, you have to, like, the longer you wait, the better the image gets, right? And because what's going on? Well, suddenly I multiplied the cost of rendering one pixel by the number of secondary rays that I just sent out, right? So I just added another constant factor to my ray tracer. Similarly, what might be a strategy for dealing with light sources? Remember, we've talked about light sources so far, but our light sources are just points, and that creates these like hard shadows, like what you see on the bottom right. But the reality is that shadows are cast by area light sources that are what makes these soft effects, like what you see here. And so here's a kind of a picture of what's going on, is that I have some area light source, and there are different regions, the umbra and the penumbra, which have to do with how much of that light you're actually receiving on the bottom surface, right? So the umbra in the shadow is the area that gets no light, and then the penumbra is where you're getting some of the light, but not 100%, right? So you have this light source, and some of it is as occluded by the surface, but other parts go through. How could I deal with this? Using the same sort of randomized strategy. Any ideas? Yeah.
So when I hit a point with my U-ray for my eye, I basically choose a set of however many random points I want from the light source area.
Yeah.
Or basically I just repeat this as many times as I want and choose random points there, and that's kind of like when it's occluded, I don't add to it, and when it isn't occluded, I kind of add to my light value, and then I kind of divide by the total number of iterations I do.
Yeah, so let's clean that up a little bit. Like essentially, if we have, we've talked about making a shadow ray. The basic question here is, what shadow ray do you choose if your light source isn't just an ideal point, right? Because remember, the direction of our shadow ray was just pointing straight toward the light source. So one thing that we could do would be to randomly draw a point on this like light source with positive amount of area, and do the shadow calculation. And as we suggest, we could do that like 10 times and average the result. And that would tell me roughly the fraction of light that gets through. That make sense? Okay, so what does that mean? Let's say I want to render a brushed material under a shadow. How much calculation do I have to do? A lot, right? Because now I've multiplied, I have to do a bunch of different shadow rays, right, to account for the area light source, and that gets multiplied by all the rays I need to deal with this noisy normal vector. I can parallelize, but it's still, I only got so many CPUs. I'm a poor professor. I'm not, one of these Google employees. let's talk about a different issue, and this is aliasing. This is something we'll talk about quite a bit, but for now we'll do a bit of a naive approach, which is roughly what people do in practice anyway. So far we've sent one ray in every single pixel, right down the center, usually, and that's the color that we assign to the ray, and that creates a particular artifact called the jaggies. And that's exemplified like on the image on the left, right? Where essentially, at the interface between a material and what's behind it, you've made this binary decision, like, am I in the sphere or not? But the reality is that like maybe half a pixel is inside of the sphere. So what could I do to solve the jaggies? How could I do better? Yes, either of you, whatever. Yeah, I could send a bunch of rays through my pixel and average their color, right? Like not just send one right down the middle. So let's say that I do maybe 10 samples per pixel, which is actually relatively low. What does that mean? Well, essentially, in some sense, I'm rendering an image which is 10 times as large, right? So suddenly, I've multiplied the computation time of my ray traced image by 10. So notice the trade-off here. Like essentially all of these nice effects that we can get in our ray tracer are just a few extra lines of code. They're really not hard to implement, right? Like randomly drawing a light direction is easy. But every time I do that, I actually incur a multiplicative factor on the amount of time it takes to generate an image. Here's another good one. Yeah.
In what way the rays are different?
Oh, sure, yeah. So remember that we're thinking of a pixel as kind of like a little square sitting in front of my eye. And so far, when we light our pixel, we just like choose a ray right down the middle. Now what I'm suggesting is to randomly draw a bunch of points in the interior of the ray, or in the interior of the pixel rather, and then average their colors. Incidentally, it doesn't even have to be random. I mean, you could put like a grid, and we'll talk about a lot of strategies later. Here's another good one. Let's say that I'm playing billiards and I want to simulate, an effect where the balls are bouncing off of one another. What could I do? Yeah. I could do what it says on the slide. That's a fabulous idea. In particular, I could essentially randomly draw the position of the balls before I do that ray object intersection every time I do for each pixel, and suddenly I have motion blur effect, right? That's great, but of course, I'm gonna have to randomly draw that a bunch of times to not just get total noise in my image, which is nice, but now I've got even more effect. Or here's another one, depth of field. So in depth of field, essentially, now I have an aperture for my lens, which isn't an idealized point, like what we talked about a lecture or two ago. So what could I do? Well, I could randomly draw some points in my positively sized aperture, and now I've got that like cute iPhone effect where things that are in the background look kind of blurry. And that's great, but the irony is that blurry stuff, which somehow feels easier to render because it looks lower detail, actually is incurring a lot of cost. Okay, so hopefully you guys get the point. Like the ray tracing assignment in this class is a lot of fun as long as you're patient, because it's really easy to code all these effects and suddenly you can get these beautiful images. You just have to wait a really long time. And there's a lot of reason for that. Essentially, every time you query a color, you tend to generate a ton of what we call secondary, tertiary rays, which have to do with all these different calculations you're doing simulating light bouncing around a scene. We still haven't even talked about global illumination, right? Like some of these weird effects like light bouncing off of the wall and onto the floor and so on. And so essentially, we have to be really careful. And we're going to talk in later lectures about strategies for making ray tracers more efficient. And those are really critical. If you want to implement a real-life ray tracer, you have to implement these different data structures to make it fast. Moreover, you have to be a little bit careful because there's so many recursive calculations that can happen here, right? Like think about, if I have two different objects, both of which are made of brushed metal and they're reflecting off of each other, like two brushed metal mirrors facing each other. Now I point my camera toward one. Well, what's going to happen? Well, I point my camera here. This launches 10 random rays off. Each of those launch 10 random rays in the other direction. We ping pong back and forth, and my code could recurse forever. I could easily blow out the memory of my laptop, all for a color which is basically nothing, right? Because every time I bounce that ray, I'm probably multiplying it by some coefficient that attenuates how much stuff bounced off. And this is a real life problem. Any ideas? How do you think we solve this problem? Yeah?
Limit the number of bounces.
Yeah, just limit the number of bounces. So a typical thing to do is to add to your recursive ray tracing code just an integer that you keep track of saying how many times have I already bounced. And if I'm beyond some number, just return 0 because like at that point, I'm not getting a significant amount of light. Okay, and of course you have to be a little bit careful with that parameter. So here, for example, we have 3, I don't know why I borrowed this figure from a really old textbook, but I did. I have 3 mirrors and a little set of balls sitting in front of it. Of course, if I have a limit of 0 for my recursion, then they don't look like mirrors. Kind of funny thing is, of course, as you change this parameter, it really does have a concrete effect on the image, right? Like whether you see the secondary thing or not. So, there's a bit of a balance to choose there, but I think typically we don't recurse a whole lot. There's one vocabulary word that we often use to kind of visualize and understand the computation that's happening here, because it is a little bit tricky. This is called the ray tree. This is not a data structure or an algorithm. It's just like a conceptual thing that we can use to kind of understand what's going on in a ray tracer. And the basic idea here is that, like, let's say that I generate a ray from my eye, like this, because I'm trying to shade a pixel. Then essentially each ray often begets many other rays, right? So for instance, to shade this pixel, I have, the ray that goes to the light to do the shadow. I've got another ray which maybe goes to another object. That one again reflects in order to do some shadow calculation and so on. And so we can keep track of this sort of tree-like structure where the root is the ray from your eye, and then the different children are like the rays that were created to shade the previous thing above it, right? And this is just one way to kind of understand this exponential multiplier that can happen. Like here maybe there's refraction, there's reflection going on, and so on. This is one way to just kind of visualize and understand the complexity of ray tracing. In fact, like here's one visualization of an object which is both reflective and refractive. So here's the ray coming in from the eye in white. And all these different colored rays are essentially showing you all the different things in the ray tree, which is some visualization of all the computation that you have to do in order to ray trace that one pixel. Right? And so now we can see why this computation gets really expensive really fast. Moreover, a big challenge in ray tracing is the following. Let's say that I've got some really complicated object, and it's really small. Right? This happens a lot. So apparently in Finding Nemo, this is a big problem because the artist got really into modeling like sea life, and it just is like sitting in the background. And like, so what would happen, like when I run my ray into Nemo, it's actually not so hard to shade. Like he's not that complicated of a fish. You don't see his internal organs, like it's fine. But then, the ray goes past the main characters into the background, and suddenly I have to intersect it with like 100 different like pieces of algae. So what does that mean? That means that the computation time per pixel can vary really widely over the image, and it's hard to predict. Right? So already a few of you have alluded to the fact that I could make my ray tracer faster by parallelizing. And you're right? I mean, if I had 10 CPUs, I could just take the pixels in my image and randomly divide them among my 10 CPUs and shade them all separately. But it actually can be a little bit challenging to do that in a balanced way. It could be that one CPU finishes a lot sooner than another, because I just had bad luck and like the really hard to shade pixel just happened to land in one CPU. And that's one of many challenges that comes up when you try to make ray tracing faster. That like some of the obvious ways to parallelize actually don't work all that well. So this is something to think about for next time, are some interesting data structures and ways that we could accelerate this algorithm in a way that is maybe amortized a little bit better over the scene and the set of rays. Okay. So that's basically it for today. Essentially, we've covered a whole variety of interesting visual effects that really are not so hard to implement in your basic ray tracer, right? Each of these is, I would say, less than 10 lines of code. Now, the thing that we've got to start thinking about is how to do that without incurring a multiplicative factor on the amount of time that it takes to generate an image. Okay, so with that, everybody download your next assignment, get started, at least make sure you can run it. We're going to do class simulation. I think that's fun. And we will see you next week. Now we turn off all the assorted streaming tools.